Welcome back. In this video, I'm going to give you a detailed description of the so-called SVPWM or State Vector Pulse Width Modulation technique as the last part of the FOC algorithm regarding the software development. As you can see on the block diagram representation, the input of the SVPWM algorithm are the controlled reference phase voltages, while the output of it are the optimized phase voltages considering the available DC link voltage. This is the last part of the FOC algorithm, which means that the function software forwards these reference phase voltages calculated by the latter mentioned logic to the base software layer, which afterwards translates these demands to direct EGBT or MOSFET switching signals for the three-phase voltage inverter. In this video, we are going to cover the theoretical background on SVPWM with the help of the Park vector representations of the three-phase voltage inverters. Let's move forward. The SVPWM algorithm is based on the fact that we would like to control a PMSM machine with a three-phase voltage inverter. An inverter is a power electronics component which is able to transform plain DC input voltage to AC alternating voltages on its output. The inverters are utilizing the so-called pulse width modulation technique, which means that the output voltage is either equals with the DC link or with ground potential while it is being modulated with a high frequency carrier. The average voltage value can be modified via the duty cycle of the PWM signal, which means that we shall control the ratio of the switch on and switch off times of a given semiconductor. These voltage inverters in the modern world are able to fulfill 4/4 drive control, which means that the controlled electric motor can work in both rotational directions in motor and generator mode as well. In other words, it means that the three-phase inverter is able to provide positive and negative phase voltages on its output regardless the direction of the phase currents, because the phase currents can both be positive and negative as well. Usually, we assume that the positive current flows towards the motor windings and the negative flows away from it. In the next slide, we are going to see that the three-phase voltage inverters are only able to output 8 different discrete voltage vectors to the controlled PMSM motor windings. The SVPWM technique considers this restriction and calculates the optimal shapes of the reference phase voltage signals to, let's say, maximize the efficiency of the control algorithm. The SVPWM is usually used in motor drive applications. However, grid inverters also utilize this method as well. This pulse width modulation technique is manipulating the stator voltage vector to regulate the controlled PMSM speed or even torque according to an external request. Finally, as I have mentioned before, the advantage of this state vector pulse width modulation technique is the ability to maximize the available DC link bus voltage on the inverter side to the motor windings. In this slide, you can see the graphical representation of the latter mentioned algorithm within the three-phase coordinate system. The A, B, and C axes are 120 electrical degrees apart from one another, and if we are considering both positive and negative values to be represented within this coordinate system, we can define 6 symmetrical electric sectors. These sectors are marked with Roman numbers from 1 to 6. Let's talk about base vectors. In case of three-phase voltage inverters, a base vector is an output voltage vector value that can be measured between the inverter terminals. Based on which EGBT or MOSFET is turned on, we can define 8 different voltage vectors whose value can be easily measured on the output terminals with an oscilloscope or even with a multimeter. Later in this video, we are going to cover the basics of these voltage vectors that can be represented in the three-phase coordinate system with a given semiconductor combinations applied. The general idea behind the inverters is that we define a high-frequency carrier signal, usually between 10 kHz and 20 kHz in case of PMSM motors, and we constantly changing which EGBT shall turn on or off in order to receive the desired reference voltage vector as an output on the inverter terminals. The resulting output voltage vector is being time modulated with the help of a high frequency carrier signal, which means that, for example, if we would like to output a vector, let's say 30 electrical degrees counterclockwise measured to the A-axis, then we shall output a V1 and V2 base vectors for the same amount of time in order to receive an average value of a 30-degree voltage vector. In other words, the V1 vector is being switched on for, let's say, 10 microseconds, while the V2 vector is being switched on for another 10 microseconds, but the main important message is that they are being used for the same amount of time in order to receive an average voltage vector between the two. So now we have a basic understanding that the angle of the resulting output voltage vector can be modulated with the help of the so-called base vectors that the inverter can directly output. Let's suppose that we would like to output a resulting voltage vector of 270 electrical degrees apart counterclockwise to the A-axis. This would mean that we shall operate in the electric sector number 5. For this, base vectors V5 and V6 shall be used for the same amount of time in order to receive an average output voltage vector between the two. When we are controlling a PMSM motor with the 3-phase voltage inverter, we shall pay attention to the time constant of the electric motor compared to the switching frequency of the inverter. This nonlinear control is only sufficient if the switching frequency of the inverter is at least 5 times greater than the time constant of the PMSM motor. In other words, the sudden jumps between the different voltage base vectors will not result in an actual rapid change in the mechanical state of the PMSM motor. If the switching frequency were too low, let's say about 10 Hz, then the motor would have an uneven jerking motion without the feeling of constant movement, which is caused by the huge torque ripples. Let's move forward and see how an actual 3-phase voltage inverter looks like in electrical point of view. As you can see, a battery package is being used in this case to define a more or less constant DC link voltage for the inverter. DC link capacitors are added to the electrical model to smooth out the sudden voltage drops of the input voltage when huge current value is being drawn from the battery package. Altogether, 6 MOSFETs are being used to build up the 3-phase inverter configuration. 3 high-side and 3 low-side MOSFETs can be seen on the picture. The motor terminals are connected between the high-side and low-side MOSFETs at each branch. The motor terminal A is connected to the first branch from left to right. Phase B of the motor is being connected to the second branch of the inverter, while the phase C is tied to the third branch. The high-side MOSFETs are marked with green, while the low-side MOSFETs are marked with purple rectangles. In this slide, you can see the latter mentioned output voltage vector representation in case of a 3-phase coordinate system. The base vectors are defined in a hexagon format listed between V1 and V6, while the zero voltage vectors V7 and V8 could be represented in the middle of the coordinate system. Now, I would like to show you how the different base vectors can be achieved by appropriate switching combinations of the semiconductors. The V70 output voltage vector can be achieved with the high-side MOSFETs turned on at the same time. In this case, the A, B, and C motor windings are being pulled up to the DC link voltage potential, which means that there is no relative potential difference between the motor terminals, so altogether no phase current is going to flow. This switching combination is often used for manipulating the absolute value of the desired resulting output voltage vector. Another possible use of such MOSFET switching combination is to actively braking a PMSM motor which is currently rotating. It is similar as if the motor terminals were short-circuited or connected together. In this case, the induced phase voltage is going to produce such phase currents that have the opposite direction compared to the actual state of the motor. This opposite phase current direction is going to produce a counteractive magnetic field, which will result in an opposite braking torque. The V8 zero output voltage vector is very similar to the V7 base vector that we have just discussed. The main difference between the two is that the previously mentioned V8 base vector is being defined as the low side MOSFETs to be switched on at the same time. In my personal point of view, this switching combination is preferred over the high side variant when it comes to braking or slowing down the PMSM machine. The SVPWM algorithm uses the high side or low side zero vectors based on the actual switching combination of the semiconductor devices. The main rule here is to always alter just one MOSFET when it is possible during any transition between the base vectors. The V1 base vector points to the A-axis direction in the three-phase coordinate system. In this case, the A phase is being excited with DC link voltage value, while the B and C phases are being pulled down to the negative terminal of the battery package. As you can see on the graphical vector representation, the numbers next to the V1 vector are 1, 0, 0. This means that phase A is being pulled up to DC link potential, while phase B and C are connected to the negative terminal of the voltage source. The V2 base vector points to the negative C-axis direction in the three-phase coordinate system. In this case, phase A and B are being pulled up to DC link potential, while phase C is connected to the negative terminal of the voltage source. In the graphical vector representation, 1, 1, 0 combination marks the previously mentioned state of the semiconductor devices. The phase A and B branches high-side MOSFETs are being turned on, while the low-side semiconductors turned off in order to avoid short circuit in case of a phase branch. Finally, the phase C branch low-side MOSFET is being turned on at the same time to allow motor windings phase C to be pulled down to the negative terminal. The V3 base vector points to the positive B-axis direction in the three-phase coordinate system. In this case, only the phase B high-side MOSFET is turned on, while at the same time phase A and C low-side MOSFETs turned on as well. I find it important to emphasize that no high-side and low-side MOSFETs or EGBTs of a given phase branch can be turned on at the same time to avoid short circuit phenomena. So, when we are talking about either a high-side or low-side MOSFET is being turned on at a given branch, it is straightforward that the other one has the opposite state. In the graphical vector representation, 0, 1, 0 combination marks the previously mentioned state of the semiconductor devices. The V4 base vector points to the negative A-axis direction in the three-phase coordinate system. In this case, the phase A low-side MOSFET is turned on, as well as the phase B and C high-side MOSFETs. In the practical vector representation, 0, 1, 1 combination marks the previously mentioned state of the semiconductor devices. The V5 base vector points to the positive C-axis direction in the three-phase coordinate system. In this case, the phase A and B low-side MOSFETs are turned on, as well as the phase C high-side MOSFET. In the graphical vector representation, 0, 0, 1 combination marks the previously mentioned state of the semiconductor devices. Finally, the V6 base vector points to the negative B-axis direction in the three-phase coordinate system. In this case, the phase A and C high-side MOSFETs are turned on, as well as the phase B low-side MOSFET. In the graphical vector representation, 1, 0, 1 combination marks the previously mentioned state of the semiconductor devices. Last but not least, let's see again the V1 base vector representation. We have completed one electric period of a phase vector using a three-phase voltage inverter device. Now, let's move forward and see how we can achieve an average intermediate output voltage vector by using base vectors. If we define a high-frequency carrier signal, usually between 10 kHz and 20 kHz, then we will be able to achieve a smooth transition between the previously mentioned voltage-based vectors without the PMSM motor even noticing it. Let's suppose that we would like to output an average 30 electrical degree voltage vector measured from the phase A axis. In this case, the V1 and V2 vectors are being used at every iteration by toggling the phase B high-side MOSFET for the same time. So it looks like this. An average 30 degree of output voltage vector is being modulated in this case, hence we are changing state between the V1 and V2 base vectors that we are giving the same amount of time to be taken for the MOSFETs when we are switching between these two states. This method can be used at any electric sectors left to constantly modulate the angle of the desired output voltage vector. So for example, if we are moving to the electric sector number 5, and we are using the V6 and V5 base vectors, as you can see currently on the slide, and allowing the system to operate between these two uh, base vectors, then if we are allowing the same amount of time to be spent in both base vectors, then an average of 270 electrical degree voltage vector will be outputted in the three-phase voltage inverter towards the PMSM machine. So this is how the SVPWM modulation altogether in fundamental point of view works. As the last part of the SVPWM algorithm, we shall get familiar with an easily implementable set of equations to achieve the desired output voltage vectors with the best utilization of the DC link voltage vector value. Within this course, it is out of scope to deduct these equations for the many times mentioned algorithm. If you would like to get more familiar with the mathematics behind the logic, I will provide necessary articles and sources to learn from. It is possible that I will create a separate video series where general equations will be deducted based on pure analytical approaches valid for PMSM machines, but for now, let us accept the system of equations that can be seen on the slide. It is good news that we shall only implement 3 equations for a given phase based on which electrical sector the reference voltage vector is in. Altogether, there are 9 equations that cover the whole 3-phase coordinate system with respect to the different electric sectors the voltage vector value is in. As you can see, for the opposite electrical sectors, the same analytical equation can be interpreted for each phase. The algorithm gives the necessary switch-on times for the appropriate MOSFET or IGBT semiconductors within the predefined inverter switching time period. The T_FOC variable is the reciprocal of the inverter switching frequency. In practice, the most used inverter switching frequency is 20 kHz, which means that the task time in this case is going to be 50 microseconds. The amplitude of the desired phase voltage is proportional to the actual available DC link voltage, which can be seen on the equations as well. Later on, when we are implementing the SVPWM algorithm in Simulink, we will look into in depth of these equations. I hope that you have a solid fundamental knowledge and understanding of the state vector pulse width modulation technique and how it is utilized in case of three-phase voltage inverters. If you have any questions, please don't hesitate to ask. See you in the next chapter. Take care.